So here we're going to describe what's a functional derivative, and we are also going to see which are the steps that you can follow in order to calculate the functional derivative. So first, the functional, it's a very simple thing. Basically, is a rule which associates a number with a set of functions, and this is this rule. For example, here we have the functional as a function of the electronic density, which is given by that expression. This is the rule here. For example, this is the Thomas Fermi kinetic energy function, which is defined and which will be defined in the Thomas Fermi model, which is considered like a first kind of density functional approximation. And we'll see that we'll use that as a reference in order to calculate the first order and second order functional derivatives of this function. Then, once we have this rule, which in this case, for example, just depends on one function, I will center the analysis in this kind of functionals that just depend on one function. We want to see what's the variation of the functional in order to calculate the functional derivatives. So the variation of the functional when the function that the functional depends on changes from f to f plus delta f, which this delta f is a small change, is defined this way, of course. Is the difference between the two. With this delta f, which is a small change of the function, we can write in this way: epsilon, which is an infinitesimal, times eta, which is an arbitrary function. So as this change here is defined in terms of epsilon, which is just basically one parameter, we can do the Taylor expansion in terms of epsilon, which is very easy to do. So this is the Taylor expansion here. Here we have the Taylor expansion of the functional f when the function f changes from f to f plus epsilon times eta. So here we have the Taylor expansion. And now we are going to make the definition of a functional derivative. And the first order functional derivative is going to be related with the first derivative with respect to epsilon. And the second order functional derivative is going to be related with the second order derivative of f with respect to epsilon. So that's going to be the definition of the first order functional derivative. So the derivative of f with respect to epsilon in epsilon equals to 0, so this term here is going to be, by definition, I'm going to write it in this way. So the integral over x1 of the functional derivative. This is the functional derivative, the first order functional derivative. Here we have, that's going to be the first order functional derivative times eta and in x1. Okay, now the second order functional derivative is going to be related with this term here, and is defined, again, that's definition, is defined in this way. So here we have that this term here in the Taylor expansion and second order epsilon is defined by the integral over x1 and x2 of the second order functional derivative. This term here should be the second order functional derivative of f with respect to f in x1 and f in x2 times eta in x1 times eta in x2. These two expressions here are the definitions of the first order functional derivative and the second order functional derivatives. So, considering that definitions here, and if you substitute in this Taylor expansion here this term and these terms here by the definitions or by the functional derivatives, so by this term and this term, that's the expression that we have here. This is the expression that we have. So basically the functional derivatives are the kernels in the Taylor expansion of the change in the functional f when the function where this function depends on changes from f to delta f. So that's interesting. So how can we calculate these functional derivatives here? So basically what we have to do is just follow the definition that we have presented above. So what's that? So let's go back. So basically what you have to do is the following. First, we are going to change f from f to f plus epsilon times eta. That's what you have to do. Then you will make a Taylor expansion. So we have a term, an expression like that, a Taylor expansion in terms of epsilon. Okay, and now you have to consider that definitions here in order to, once you have these two terms calculated, this one and this one, considering these two definitions, you can extract from this definition what's the functional derivative, the first order functional derivative and the second order functional derivatives. So let's do an example, basic simple example. For example, here we are considering the function we have defined above, which is the Thomas Fermi kinetic energy functional, which again appears in the Thomas Fermi model. That's not important here. So we are considering this functional here, which again it represents like kinetic energy in terms as a functional of the electronic charge density. So here, and we are going to make the functional derivatives of this f with respect to n, the first order functional derivative and the second order functional derivatives. So the first thing we have to do is we are going to change f, in this f, we are going to change eta, the density n with n plus epsilon times eta. That's what we are going to do. And we're going to subtract with respect to the f we have when you don't have this change. So basically the change on f, when the functional, when you make that substituting, you change n with n plus epsilon times eta, that's the result you have. Now you're making the Taylor expansion with respect to epsilon. That's very easy, that's the term you have here. And that, considering that Taylor expansion, you go just order by order. You just have, for example, the linear term, consider the definition with the first order functional derivative, and from that definition you can extract that the first order functional derivative is given by this term here. Again, you go to second order in this Taylor expansion here, you consider the definition of the second order functional derivative, and you can easily extract that the second order functional derivative of f with respect to the density is given by this term here. So that's basically here. Now we know what's a functional, and we know what are the definitions of functional derivatives, and it's a way, and we know a way to calculate them. Even though this is not such a straightforward method, so we are looking for like a more straightforward method to calculate these functional derivatives.